Almost any MCU has a hardware debugging capability. This complex technique requires an external debugger using an interface such as JTAG. Setting up hardware and software for simple projects may not be worth a penny, thus the most frequent case is tracing over debugging. Tracing uses a technique where the developer explicitly sends some data to the external device, such as a PC or a dedicated terminal. The use of the serial port for tracing is common because it is the one that is most frequently used for programming, so in reverse it can be used for tracing. The Arduino framework provides a dedicated Singleton object, instantiated automatically, that represents the serial port. It can be physically the same port that was used for programming or another. Moreover, some software development kits and Arduino frameworks implementations provide the ability to declare more than one serial port so that the user can redirect traces visually to some other port and external device than the one used for flashing a device. To use the serial object representing the COM port used for tracing, it is necessary to initialize it to provide at least the COM port speed. Communication parameters must be agreed with an external device such as a PC that the IoT MCU is connected to for tracing or communication purposes. It is usually done with once per source files in the setup function. Standard communication speed used to be 9600, but also 115200 is also common. In the case of the tracing, it is usually configurable in the terminal software on the development computer. In particular, Platform I/O is configured in the platform.io.ini file per project, and the default speed is 9600 bits per second. The serial class Singleton has several member functions, but perhaps the most important for tracing purposes are serial.print and serial.println. The last one prints the message to the serial port, including the new line character. The serial class also includes a set of functions that enable data to be read from the serial port. It can be used for remote control of the device or to implement communication with another component, such as a GPS module that uses the NMEA serial protocol. The most useful here are serial.available that returns a number of bytes received from the remote device, serial.read that reads one character from the incoming data buffer, serial.readString that simplifies reading of the string data. Another challenging task is handling hardware switches. The use of buttons is common in the implementation of the user interfaces. Depending on their physical construction, hardware buttons tend to vibrate during a switching, which is called bouncing. This is observable on the MCU side as a series of pulses instead of a single state change. For this reason, debouncing mechanisms are introduced. The majority of the buttons operate so that when opened, the logical input read by the MCU is 1, which is high. When pushed, it is 0, which is a logical low. It is due to the use of an internal or external pull-up resistors and connections present in the schema. A dummy approach to solve this problem is to read a button in the loop function of the application and check its state with some predefined delay that is commonly known for the bouncing phenomena to stabilize and disappear. The typical period is in between 50 and 200 milliseconds. This algorithm presents on the listing, while simple, has a serious drawback. It blocks program execution. Moreover, there is no guarantee that the algorithm will succeed, because it strongly depends on the moment of the button press or release versus the current progress of the blocking period. A better approach is to use a finite state machine approach, which is more reliable and easily extendable by detecting features such as double button press, long press, and so on. In this algorithm, we use either a non-blocking reading of the state or rather the use of the hardware interrupts that trigger the state machine. The sample algorithm is presented on the screen and it can be easily implemented as a class. In the simplest case, the state machine identifies three distinguishable states for the button: released, debouncing, and pressed. Note that this is not exact representation of the physical state of the button, but rather its representation after passing via the low-pass filter. The use of class helps to handle multiple buttons and hardware-specific configurations such as the bouncing time.